done it at least once. Where they've, not saying me specifically, but a teacher.
I've called Frau Jones' mom a couple of times.
Yeah.
Not in German though. Just mom.
Yeah. That involves way too much thought, and it's not the instinctive response. I think if you did, you should get an extra credit point. If you called her mother in German. Because it means you're thinking in German. All right. So we're going to work with Descartes' rule of signs, which we should have most of it written down. I know it's a lot of words. It's honestly a fairly simple concept. Because what this is a way to estimate or to figure out the signs of our solutions. So the number of positive real zeros is either equal to the number of the changes in the sign or less than that by an even. So what we're going to do is we're going to take this polynomial down here and we're going to count how many times the sign changes signs. Which that was a whole lot of words of the same word. So we're going to look at this and say, all right, x to the fifth is positive, and then it changes to negative. So it changes sign once. And now it's negative, and it changes sign again. So that would be 2. And then it changes sign again, so that's 3. And let me get another color. It changes sign again, so it's 4. And it changes sign one more time, so there are 5 sign changes here. All right, you see that? The sign changes? There's 5 of them. That means there are either 5 positive real roots or less than that by an even number. So 5 or 3, less by an even. So go down by 2s. 5 or 3 or 1 positive real roots. And all that means is our solutions are positive. This is going to have at least 1 positive real root. It might have 5 positive real roots, but it's going to have at least 1 positive real root. This does not give us any clue as to what our positive real root is. It could be 1, could be 5 million, could be 0.00000000001, but it's somewhere positive. But other than that, we have no clues. So it's a very similar thing for the negative real roots, negative real zeros, except we have to put opposite of f of x in, just like when we would do for like testing for our symmetry or testing for any of that stuff. We've done that repeatedly. So we're going to use our same f of x, and we're going to substitute in the opposite of x. There we go, purple. So when we substitute in the opposite of x, we're going to have the opposite of x to the 5th minus the opposite of x to the 4th plus the opposite of x to the 3rd. Except I put that one in the wrong spot. There we go. Opposite of x squared plus the opposite of x minus 1. Whew, lots of stuff. We're going to see which ones of these we can simplify. The opposite of x to the 5th is this. What can we simplify this down to? Negative x to the 5th, or the opposite of x to the 5th. Dude. On your video, I can hear it up here. I don't know what goats you're watching, but whatever. Sounded like a goat. None goats. All right, how about our opposite of x to the 4th? it's going to be, yeah. Since it's an even exponent, that negative cancels out, so we just have minus x to the fourth. How about our opposite of x to the third? Yeah, we're just going to have minus x cubed. Opposite of x squared. We're just going to have minus x squared minus x minus 1. So we've done things like this before. We did this when we were checking for like even and odd, checking for some symmetry. So we've done this on a few different things. How many times does the sign change? None. There are no sign changes here. Since there are no sign changes, and I know I'm right at the bottom of the screen. Since there's no sign changes, that means there's no negative real roots. I don't know why I have 2 L's on the word real. There we go. Spelling is a suggestion. Dude, why are you texting so much? Thanks. You've been checking the time then for 5 minutes. I should also be taking notes. Thank you. All right. So that's what we're doing with Descartes. Counting the positive real roots and changing the negative real roots. Okay? We're going to practice this a couple of times. We're going to figure out how many positive real roots, how many negative real roots, and then however many are left is how many complex roots we might have. So here's our first function. F of x equals 4x cubed minus 6x squared plus x minus 3. Write it down. What's up? So first things first is to figure out how many positive real roots we're going to have. So from our function rule as it is, as we are given it, how many sign changes do we have? So we have 1 here, 1 here, 1 here. There are 3 sign changes. That's an H. There we go. Which means we have 3 positive real roots, or 1. We're either going to have 3 or we're going to have 1. To figure out how many negative real roots we're going to have, we need to substitute in, on a different color, the opposite of x. So we're going to do 4 times the opposite of x cubed minus 6 times the opposite of x squared plus the opposite of x minus 3. I recommend writing this step out, at least as we're getting started with this. Don't try and do the whole thing in your head. Four times the opposite of x cubed. How can we simplify this piece? Negative 4x cubed. How about minus 6 times negative x squared? I'm going to have minus 6x squared. So the 6 is not included in the square. It's just the opposite of x that's being squared. Ooh. So it's just the opposite of x being squared. So that negative 6 is still negative. Plus the opposite of x, minus x, and minus 3 doesn't change. So this is f of the opposite of x. How many sign changes do we have here? None. There's no changes. And those words are smashed together, but there's no sign changes. So how many negative roots do we have? 0. None. If there's no sign changes, there's no negative roots. So then what we're going to do is we're going to list out all the possible options for the ways we can kind of set up our roots. Our zeros are either going to be positive or negative or complex, like imaginary, right? I'm going to put non-real. So it's positive real, negative real, or not real, imaginary or complex. No matter what, how many roots are we going to have? How many roots is this function going to have? 3. No matter what, we need to have a total of 3 real roots, right? I will move the page up. I see everybody doing the kind of dodge in the back. So it could be that we have 3 positive real roots. We're going to have no negative real roots. How many complex roots are we going to have if we have 3 positive roots? 0. Or we could have 1 positive real root. We're still going to have no negative roots. How many complex roots would we have then? 2. Because we still need to wind up with a total of 3. No matter what, we need to wind up with a total of 3. That's our degree. So we're just going to list out all the options. Questions on that one? Because it's the first time we've gone through the whole thing.
I'm not understanding the 3 or 1. Why is it 3 or 1?
Because it's either however many changes it is, or it's less than that by an even number. So subtract 2. Count down by 2s. Yes, dear.
Why is it not 0 and 2?
Because we have to have a total of 3 roots. Whenever whatever our degree is, that's how many roots we have to have, right? So if I have 1 real root that's positive, I have no negative roots, I have to get the 3 somewhere. So they're going to be imaginary. Good questions, guys. Good questions. We're going to try it again. I promise. Okay. Same thing. This one's just longer. So we're going to figure out the number of possible roots, whether they're positive, negative, or not real, for this function rule. F of x equals 3x to the 7th minus 4x to the 4th plus 3x cubed plus 2x squared minus x minus 3. Whew, long one. I'll give you a second to write it down, because I know y'all don't have it reprinted. Oh, snap. What's that?
So, is that the highest, number?
The highest exponent.
The changes always going to be the highest exponent?
No, the degree is always the highest exponent, sorry.
Because for
this one, I know like it was extra faint when I see like we changed it.
It's not gonna always match.
Alright.
It just happened to match on that one. All right. You have it written down? Okay. How many changes does f of x have? We have 1 here, 2. Is that the last time the sign changes? Got 1 more over here. So we have 3 changes. Which means our positive roots, how many could we have? 3 or 1. We're going to have at least 1 positive real root, but at most 3 positive real roots. So then we're going to substitute in that opposite of x. Oops, sorry. So we're going to do f of the opposite of x. Substitute that in. Three times the opposite of x to the 7th minus 4 times the opposite of x to the 4th. 3 opposite of x cubed plus, ooh, I'm going to run into stuff. 2 opposite of x squared. I'm going to tilt mine a little bit. Minus the opposite of x minus 3. So you can tell I zoom in a little bit too far and I run into the stuff I've written. All right, then let's simplify this so we can look at our signs. 3 times the opposite of x to the 7th. Negative 3x to the 7th. Minus 4 times the opposite of x to the 4th. Is this going to have a minus or a plus between the two terms? A minus. Because the opposite of x to the 4th, that just becomes x to the 4th. So the sign does not change. How about on 3 opposite of x cubed? It's going to have a minus here. Positive on the 2 times the opposite of x squared, because the sign is not going to change. How about on minus the opposite of x? For me, it's on a kind of diagonal. Plus x. It's called, I was trying not to write over the words I've written, but it happens. And then we have minus 3. So on our opposite of f of x, or f of the opposite of x, there we go. How many sign changes do we have? 2. So I've got this minus to plus, plus to minus. So we only care about when it changes. So our negative roots, how many negative roots are we going to have? 2 or 0. Yes, sir. If it was negative 4, opposite of x to the 4th, like negative 4 being in the parentheses, then yes. But since the minus 4 is not included in the 4th power, that minus sign still hangs around. So since we are substituting the opposite of x just in for the x, this minus sign still is outside. So it's one of those be super careful situations. Okay, so questions on that part? Because now we're going to make a list of our possible options. So, how many roots are we going to have total? Seven. I heard it once, but I was waiting for more people to say it. Okay, so we are always going to have a total number of roots that's equivalent to our degree. Every single time. Every single time it's your biggest exponent is your total. So we're going to have some number of positive roots, some number of negative roots, and some number of complex roots, or not real. And no matter what, we should have a total of 7. So we're going to have a lot of different combinations we can have here, and we're going to list them all out. We could have 3 positive real roots. We could have 2 negative real roots. How many complex roots are we going to need to have? 2 to get a total of 7. Right? We could have 3 positive roots and no negative roots. How many complex roots would we need there? 4 for a total of 7. Maybe we don't have 3 positive roots. Maybe we only have 1 positive root. We don't know. If I have 1 positive root, maybe I have 2 negative roots. How many complex roots would I need here? 4, because we still need to have a total number of 7. Maybe I have 1 positive root and no negative roots. How many complex roots do we need here? 6, because no matter what, I need to have a total of 7 roots. And those are all the possible options for how many roots there could be. This just tells us whether they're positive or negative. They're not telling us where, just above the y-axis or below the y-axis, which I just did backwards for y'all. Yes, dear?
How do you know that 2 is the amount of negative roots?
Because this changes sign. Because it's negative here, and it changes to positive, and then went from positive to negative. So there's 2 sign changes. Because we had 1 sign change here and another sign change here. It's all about the sign changes. And this one we had 1, 2, 3 changes. Okay. F of x is always going to tell us how many positive roots it is. F of minus x tells us how many negative roots it is. Every time. Good questions, guys. Where I put this one? Ooh, love it. I don't know that actually. All right, one more of these. Practice it one more time. And then we'll go on to the next thought. Because we got more things to do. Oh, I love it when I don't write it down in my notes and I get to do it for the first time with you. So much fun. Yay, experiments. All right, so f of x is x to the 4th plus 7x cubed minus 4x squared minus 7. Okay, yeah, no, we didn't do this one. Just felt really familiar. I don't know why. I feel like I've done it. I guess I didn't. Alright, coffee's done. Alright, so for our positive roots, how many sign changes do we have here? Just 1. 1 change So that means how many positive roots are we going to have? Just one. I don't know why I put it in parentheses, because I made a choice. There we go. So we're going to have one positive root. F of minus x. We're going to have the opposite of x to the fourth plus 7 times the opposite of x cubed minus 4 times the opposite of x minus the opposite of x minus 7. Substitute in your opposite of x in place of the x. Then we're going to simplify it. Opposite of x to the fourth is just going to be x to the fourth. Plus 7 times the opposite of x cubed. Minus 7x cubed. Minus 4 times the opposite of x squared. Helps if I put the exponent on it. Minus 4x squared. Because this negative sign winds up canceling out with itself. That one still is in play. Minus the opposite of x. Plus x. Good. And then minus 7 is just coming on down. How many sign changes do we have here? 1, 2, 3. So we have 3 changes, which means for our negative roots, what are our options? We're either going to have 3 negative roots or 1. So when we make our list of options with our positive, our negative, and our complex, I'm going to give us more space at the bottom, which means I'm going to change our view so you can actually see what I'm writing. How many total roots do we need to have on this? 4. So no matter what, we need to have a total of 4. We know we're going to have 1 positive root. It's the only option we have. We have to have 1. Maybe for our negative roots, we have 3. So how many complex roots are we going to have? None. Only real roots. Huzzah! But maybe we have 1 positive root and only 1 negative root. How many complex roots would we have then? 2. Do we have any other combinations we can make? Nope. That's the number of options we have for roots. Okay? So Descartes is not super duper complicated. It's just a little weird to wrap your brain around. And then you go, why did we figure this out? It's called before the days of the internet, they would get real bored. Yeah, pretty much.
I mean, people still are mathematicians that discover random things.
They do indeed.
How many more questions do we have?
Well, it just depends on how much time we got. We still got 15 or 10 minutes. We're not done. We're not done. But we are going to take the first thing in 4-4. That was the end of 4-3. And this is another definition that's super duper wordy, but is actually something we've already talked about. It's just got a fancy schmancy name on the conjugate pair zeros of a polynomial. This is 4.4. So this is the first start of 4.4. 100%, this is stuff we've done before. What this is talking about is that our complex roots always come in pairs. The imaginary roots, remember when we had 3i? It was always plus or minus 3i. The same's true with a complex. It's not just imaginary. Oh, I love it when it plays games with my formatting. This is 100% supposed to be real numbers, and that little line down below is supposed to be on the R. There we go. So it has coefficients of real roots. So if we have a complex root, if you get something that's a complex number, a plus bi is generally how we write it. It just means something that has an imaginary root. That means you also are going to get minus bi. The second paragraphy looking thing is the instructions for the problem. Write an equation in factored form to start that has a degree of 4 and the zeros of 2, -1, and 3i. So we're starting with factored form, writing out our roots like this, which should seem very familiar because we've already done that at least once. This is just the formal definition of why we did that. That our imaginary roots, our complex roots, always come in pairs. So what we're going to do is we're going to write this as a f of x equation. So it says product of linear and quadratic polynomials. So product means things that are multiplied together, right? Things that are multiplied together is factored form. So this means factored form. So first things first, how do I write a factor that has a 0 of 2? X minus 2. How do I write a factor that has a 0 of -1? X plus 1. Easy questions, right? Whenever we have an imaginary root, 3i, that means we're going to have two roots there, plus and minus 3i. Whenever you have imaginary root, its conjugate is also a root. So I'm going to write this as x plus 3i and x minus 3i. Right? Makes sense. We still got those two roots. We do at this point wind up with 1, 2, 3, 4 x's, so we've hit that degree 4. However, have you ever seen a polynomial with i's in it? No. Multiply the two things with i's together. Our conjugate pairs, multiply them together. Because if we notice, this is a difference of squares pattern, right? Mm-hmm. So this is going to wind up being x squared minus 9i squared, right? So it still has i's in it, but we can simplify this. What does I squared equal? -1. So this is really x squared plus 9. I'm going to drop my other two factors. X minus 2, x plus 1. Give it our function rule. And we now have f of x is a product, things being multiplied, of linear and quadratic functions. That's what it means. I will scooch it up for you. That's what it means when they say express it as a product of linear and quadratic polynomials. Factored form. That's all it means. It's just, again, sometimes slightly overcomplicated. Always. Always. I's will always come as plus or minus. They might not say it, but that's what that theorem is telling us. Okay? We'll do one more of these, and then we'll be done. Okay? That'll put us in a really good place for Monday.
Go back.
Yes. Absolutely. Always. All right. So same instructions. Again, it looks like a lot. Oh, and it played games with my formatting again. We love that so much. So we have degree 3 and 0, 0 and 4 minus I. So this one's real. So how do I write a factor that has a 0 of 0? X. Ta-da. We did it. The theorem we just had took our imaginary root, and its conjugate is also a root. So 4 minus I is a root. That means also 4 plus I is a root. That's what our conjugate pair theorem was saying. So if 4 minus I is a root, 4 plus I is a root. And we're going to set them up just like we do our normal polynomial roots. X minus 4 minus I and x minus 4 plus I. I got it. Hello, darling. And you were at the CCRT thing?
Yeah.
Okay, cool, cool.
Did you need the pass?
No, just toss it. Oh, sorry, my screen just likes to freak out whenever I try and open Skyward at the same time.
It's not.
Oh, you're right, it's on the wrong page. There we go. We love it when my projector likes to make its own choices. So much fun. Okay, so again, we don't like polynomials with i's, and this one looks particularly gross. So we're going to multiply it out. So we're going to take, and first thing I need to do is distribute the minus sign on both of these. X minus 4 plus I and x minus 4 minus I. And we're going to multiply these together. We're just going to go carefully and organizedly. It worked, I'm taking it. So we're going to have our x times x, which is x squared. X times minus 4, minus 4x. X times minus I, minus ix. Gross, but it's a thing. So minus 4 times x, minus 4x, minus 4, plus 16, minus 4 minus I, plus 4i, and then the i's, ix. I times minus 4, and I minus I, minus I squared. Oh, we love it. I'm on a level line again. And we have a lot of pieces, oh, not that one, that cancel out. My 4i and my minus 4i, my ix and my minus ix. So this factor is going to become x squared minus 8x And we have plus 16 and minus I squared plus 17. Because I squared is negative 1, minus negative 1 becomes plus 1. So this is our full factored form, and we made it before the bell. Woohoo! We made it. Barely, but we made it. All right, we will keep going with 4-4 on Monday. Putting it up there just so that y'all don't get grumpy because you get mad at me when I don't put it up there. Yes, dear. For what?
To like go over all of that.
I was like, I'm giving tests in all my other classes, so I'm gonna have a bunch of people in here testing. I was like, I only open for tutoring during 5th period on Wednesdays.
Okay.
Okay, so I'm after school on Mondays or 5th period Wednesdays. Okay?
Thank you.
You're welcome, my dear.